Hello and welcome to lecture 12 for the course ECE 254B Parallel Processing. In this lecture I will cover chapters 11 and 12 in the textbook. Chapter 11 basically gives us a taste of numerical algorithms on 2D meshes. And chapter 12 basically puts together everything else we need to know about meshes, the sense of the variants and uh, architectures that are related to the 2D mesh. So let's start by examining some numerical algorithms. In chapters 9 and 10, we dealt with sorting and data routing. So the algorithms are basically non-numerical in nature. So this is the first experience with numerical algorithms on meshes. And the algorithms that we will consider are matrix multiplication, solving triangular systems of linear equations, solving tri-diagonal systems of linear equations. So these are special cases that are simpler, and then arbitrary systems of linear equations. And finally, a couple of graph algorithms and the one image processing algorithm. So these last two are not really numerical. You can call them semi-numerical because graphs and images are represented as matrices with numerical entries, but the nature of the algorithms performed on these matrices is not numerical in the sense of involving heavy arithmetic. Okay. Let's start with matrix by vector multiplication on a linear array. So we want to compute y equals a times x. A is a square matrix, n by n, let's m by m, and x is an m vector, and the result y is also an m vector. And by definition, matrix by vector multiplication is given by this equation, where the ith element of the result vector is basically summation of aij xj. So it involves m multiplications and m additions. Therefore, the total complexity is order m squared. Order m squared arithmetic operations. So let's assume that we have m processors. So the number of processors, the number p of processors is equal to m. So in this case, I've chosen a small example. A 4 by 4 matrix A is being multiplied by a 4 vector x. Basically, y0, for example, the output, according to this equation, is a00 x0 plus a01 x1 plus a02 x2, I is 0, plus a03 x3. So this processor basically computes y0 by receiving a00 and x0 at the same time, multiplying them. So if some running total is initialized to 0, then to that is added a00 x0. On the next clock cycle, so these elements enter 1 per clock cycle. A01 enters from above and x1 enters from the left, so you have a01 times x1 plus a02 times x2 plus a03 times x3. So once x0 enters here, it's passed on in the next clock cycle to this next processor. That's why the elements of the matrix enter 1 clock cycle later. So there's 1 clock cycle idle time, and then x0 arrives here in the next clock cycle, and A10. So A10 x0 plus A11 x1 plus A12, and so on and so forth. Okay, so this is the matrix. This is row 0 of the matrix, and this is column 0 of the matrix. That's the dashed line, dash diagonal line. Okay, so the time needed to complete this operation, this is the processor that finishes last. This one finishes first. And this one basically has m minus 1 idle cycle plus m computation cycle. So the total running time is 2m minus 1. Therefore, it's order m. The running time is order m. Remember I said that the sequential solution is order m squared. So we are basically achieving order m speed up by using m processors. This is another way of looking at that solution. So this is the matrix. This is the vector by which it is multiplied. And this is the result vector. This vector, input vector, is input here, one element at a time. x0 first, then x1, then x2, then x3. And rows of the matrix are input to the corresponding cells here, with each subsequent row delayed by one additional unit. So those delay elements that you see there, so this is sort of drawn in terms of the circuit representation. Okay, so you see here that row 0 of A enters P0, row 1 enters P1, and so on. This is exactly the same thing, just drawn in a different way. Okay, now matrix by matrix multiplication can be derived from the previous architecture quite easily, because if you multiply matrix A by matrix B to derive matrix C, basically a particular column of matrix C is equal to A multiplied by the corresponding column B. So A multiplied by column 0 of B gives you column 0 of C. Multiplied by column 1 of B gives you column 1 of C, and so on. And because the A elements that come into the top row are passed on to subsequent rows with one clock cycle of delay, the elements of each column is delayed with respect to the previous one by 1 unit. So this is delayed by 1 unit, the next one is delayed by 2 units, the next one by 3. Now the running time here, basically this is the processor that finishes last. By the way, the elements are computed within the processors. We assume that they're not output. So C00 is computed here. Okay, basically by multiplying A00 times B00, A01 times B10, A02 times B20. Notice here that IK times BKJ, AIK, so the K part, so 0000, oops, sorry. Okay, sorry. A00, B00, A01, B10, A02, B20, A03, B30. And similarly, so the elements of the result matrix C are computed one per processor. Now, as I mentioned, this processor at the lower right corner finishes last. It has an initial m minus 1 units of delay. Then m inputs come in, and again it takes m minus 1 step for these inputs to propagate down here. So the total time is 3m minus 2. It's still order m. So basically, matrix multiplication is order m cubed on a sequential machine. It's a sequential algorithm. So here we have m squared processors, and we have an order m running time. Okay, now if the x values are stored rather than input, see in the previous algorithm, in this one, oops, x values are input and a values are input. Now in this variant here, we are assuming that the x values are stored in the processors and the a values come in. If we do it this way, then we gain the advantage that no delay is required for the a inputs. Therefore, the running time will be m instead of 2m minus 1. Okay? And the reason for that is that these multiplications can be performed in any order. We don't have to do AI0 times x0 first, and then AI1 times x1. We can do it in any order. So the way this is organized, this computation is organized, x0 is here, x1 is here. Okay, so this is, let's say, at some given time instant. Okay, and then the x values rotate. So in the next clock cycle, in the current clock cycle, I'm computing x3 times a03. In the next clock cycle, x will be shifted, so x0 will enter into this cell. So this will be now x0 after a rotation. And that x0 will be multiplied by a00. And then another shift, x1 will come here. That x1 will be multiplied by a01. Okay, so each of these processors does its multiplications in a different order, but it will do, each of them will do the m multiplications required, and therefore in m cycles, all the multiplications are done and the corresponding additions are done, and the output becomes available in all the cells. Okay, well, we can use that idea to multiply two matrices that are already stored in the processors, in the cells for a 2D mesh. And so this is a particular instant in time where each processor contains one element of the matrix A and one element of the matrix B. The A values, elements of matrix A, are rotated along the column. Elements of B are rotated along the rows, and these rotations basically force the required elements to meet in the appropriate processor and to be multiplied together. So at this moment, you see that, for example, this processor, the elements are hidden because I've shaded this, sorry for that. But let's look at this processor. This processor has A00 and B03. So it multiplies A00, B03. So that's one of the 4 multiplications that needs to take place. Then the A values rotate column-wise. So the next value to come here is A01. And the next B value to come here comes from here, B13. So A01, B13. Then A02, B23. And then A03, B33. So all the 4 multiplications take place in the cell and they're added together. Okay, so the running time of this algorithm is m steps rather than 3m minus 2, which was the case when these inputs would come in and had to be passed from one row to the next. There was additional delays there. But in this way, provided that the 2 matrices are stored according to the pattern that you see here, in m steps, m multiply add steps, all the required operations are performed and the matrix multiplication is completed. Okay, in the next section we talk about solving triangular systems of linear equation. So a triangular system of linear equation looks like this. Basically, the coefficients of the equations form a lower triangular matrix. So basically, the non-zero elements are on the diagonal over here and below the diagonal. Everything above the main diagonal is 0. So that's basically why we don't have all the variables in this area, the blank area. Okay, now solving such equations is simple, even if we have to do it manually, because from the first equation, we can obtain x0. There's just one unknown, x0, which is b0 divided by a00. Once we know x0, we can substitute in the next equation, and so this becomes a number. We take this number to the other side, and then there's just one unknown x1, which we can compute. This is known as forward substitution. So we find x0, substitute forward into the next equation, then x0 and x1 will be substituted forward into the next equation, and the variables are found one at a time. So it's pretty easy. So this is an order. If the coefficient matrix is m by m, this is order m squared. Okay, so you need just one operation to compute x0, just one division. Then you need multiply, subtract, and divide for the second one. So the number of operations increases as we go down. So that's why it's order n squared. Or m squared, I should say. These are m by m matrices. Okay, we also may have an upper triangular matrix, which is just the opposite. The last equation has just one variable, the next to the last has 2 variables, and so on. So in this case, the process is called back substitution. Not that it is different, it just has a different name. So from the last equation, we find xm minus 1, then substitute in the equation before that and find xm minus 2. So back substitution refers to this process, and forward substitution to this one. Unfortunately, in the textbook, I've used back substitution erroneously to refer this, but it's not a big deal because the 2 processes are similar except for the direction of movement. So this is forward substitution, this is back substitution. Okay, so we know how to solve this manually, or very easily we can program it on a sequential computer. So this is basically a linear array used to implement this forward substitution. From the above, we receive the triangular matrix. From the left, of course, the x's are what we are trying to compute, so the x's are not known. These are just placeholders. Basically, they indicate timing. So the first thing we do, we compute x0. And x0 is computed by dividing b0. So the b values, the right-hand sides of the equation. These right-hand sides, the b values enter from the right, the coefficient matrix, which is triangular, lower triangular from above, and these placeholders for x's from the left. So we first compute x0 as b0 divided by a00. So this cell performs a division. Okay, and notice that inputs come in on every other clock cycle. So these dashes represent idle cycles where no input is presented. Similarly here. The reason for that becomes clear in a second. So once x0 is computed and its output, then the value x0 just computed is passed on to this cell. Meanwhile, the b values move and b1 is now sitting here. So x0 comes here, b1 comes here. So b1 is multiplied by x0, and at the same time a10 comes up there. So this cell, each of these cells, except for the leftmost one, which just does a division, computes the following: b minus a times x. So the right input minus the top input multiplied by the left input, and passes it here. So this one will compute b1 minus a10 x0. b1 minus a10 x0, and then it divides that. Later we'll divide it by a11, which occurs here. So in the next cycle, a11 comes in. So this thing, which now it's no longer b0, it's now b1 minus a10 x0, this value is divided by a11 to give you x1, and so on and so forth. So we need these spacings or idle cycles because basically the value x0 computed here goes to this cell and then has to come back to this cell before the next division occurs. And that idle cycle, when this cell is idle, this one is doing its job. This one is idle, this one is doing its job. Okay, so every other cell is idle in any given cycle. Okay, so if we want, we can basically use another triangular matrix in these blank spaces and solve a second triangular system of linear equation by taking advantage of the idle cells. So when one triangular system of linear equations is using this cell and this cell, the next one will be using this cell and this cell. So all the cells will be busy, and we'll do in roughly the same amount of time, we'll solve two triangular system of linear equations. Okay, this gives us an idea for triangular matrix inversion because, so this is a lower triangular matrix, and this is the inverse matrix which we are trying to compute. It's unknown. Focus on one particular column of this. By definition, you know, this matrix multiplied by its inverse gives you the identity matrix. Okay, so if I want to compute the first column, this matrix, so these are unknowns, my x's. This is basically a linear system of equations where this is the coefficient, these are the unknown, and this column is the right-hand side. The next column, this is the coefficient matrix, these are the unknown, this is the right-hand side. Okay, so each column of the inverse matrix is determined by solving a triangular system of linear equations, the right-hand side being the different columns of this identity matrix. So A multiplied by the ith column of X yields the ith column of the identity matrix. Okay, so therefore, um, computing this inverse reduces to solving concurrently several linear systems of equations with the triangular coefficient matrix. And this can be done by a mesh-connected computer as shown here. So this is basically the triangular coefficient matrix. These are the various columns of the identity matrix coming in. So the values actually input are zeros and ones corresponding. So this is column 0 of the identity matrix. This is column 1. This is column 2. This is column 3. I've given these general names because these values change as they go through. Okay, so row 0 solves for column 0 of the inverse matrix, row 1 solves for column 1, and so on. So it's pretty easy to understand. Again, because the A values enter each subsequent row with 1 unit of delay, these placeholders for the X values are delayed by 1 extra units per row of the matrix, row of the mesh. Okay, there's just one optimization here. Remember that here we had a divide in the first cell and then multiply, subtract. Okay, because this A00, instead of dividing by A00, I can compute the inverse of A00 and then multiply. The advantage of that is that this division to compute this inverse is done only once, and then the subsequent rows can do multiplications instead of divisions, which are simpler operations. So in the first row, I compute the inverse of AII, and then multiply that by this value. So instead of dividing this value by A00, I compute the inverse of A00 and then multiply this. So this cell has an inverse computation circuit and a multiplier. Each subsequent row has just a multiplier because the inverse has already been computed in the top row. Again, we can invert two matrices by using these idle slots to input another triangular matrix and another set of placeholders for the inverse matrix. Okay, so that was one special case where linear systems in which the coefficient, matrix of coefficient was lower triangular. Upper triangular is similar. A tri-diagonal system of linear equations basically have a coefficient matrix in which all the non-zero elements are on the main diagonal, the diagonal just above it, and the diagonal just below it. In other words, everything else in the matrix is 0, except possibly some of these may also be 0, but all the non-zero elements are concentrated on the main diagonal, the diagonal just above it, and the diagonal just below it. So this is called the tri-diagonal matrix. There are 3 diagonals that hold all the non-zero elements. So this coefficient matrix multiplied by the vector of unknowns gives you the right-hand sides. Okay? Now, unlike the tri-diagonal, first of all, the first equation has 2 terms. So d0 x0 plus u0 x1. The last one has also 2 terms, and every other equation has 3 terms. Okay? To make things uniform and make things easier, we just introduce this dummy variable x minus 1, whose value is of no interest to us. We just include it there. So for example, we can set L0 to 0, so that every equation has now 3 variables, and also this dummy variable minus 1, or sorry, dummy variable xm just beyond, so the variables are x0 through xm minus 1, and then we add x minus 1 and xm, and this term again we can set to 0. This way every equation has 3 terms and we can treat them uniformly. Now whether 2 terms or 3 terms, we cannot, there's no obvious starting point, unlike the tri-diagonal systems, because our equations contain 2 or 3 actual variables, and there's no place where we can find the value of one variable and substitute in the other ones. So the question is, how do we solve this? There is a very neat scheme for solving this. By the way, tri-diagonal systems have applications in solving differential and partial differential equations. And there are a number of other applications. Sometimes we don't have tri-diagonal matrices, but like this one, pentadiagonal. So there are 5. The main diagonal, one above it, and the one above that, the one below it, and the one below that. 5. There are 5 diagonals that contain the non-zero elements. Now, if we divide this matrix into 2 by 2 blocks, this turns into a tri-diagonal matrix in terms of those 2 by 2 blocks. Okay, so the methods that I'm going to describe will be applicable to a pentadiagonal matrix, or even with more, with this block trick. Use blocks instead of single elements to turn this matrix with a larger number of diagonals that contain non-zero elements into a tri-diagonal matrix. Okay, so the method that is used for solving such equations is called odd-even reduction. You divide the variables into even index like x0, x2, and so on, and odd index x minus 1, x1, x3, and so on. Okay, from the odd, so this is equation 0, this is equation 1, equation 2. So equations are also numbered. So there are even indexed equation 0, equation 2, and odd index equations, equation 1 and equation 3. So an easy way to remember, the equation number is the index of the middle variable. So the middle variable in this equation is x1, so we call this equation 1. This is equation 2 because the middle variable is x2, and so on. So from the odd indexed equations, find the middle variable in terms of the other 2 variables. So find x1 in terms of x0 and x2. Find x3 in terms of x2 and x4. Okay? So basically, this is how we compute x1. d1 x1 is b1 minus l1 x0. Oops. Minus u1 x2, and then divide both sides by d1, and you get x1 in terms of x0 and x2. And you find x3 from this equation in terms of x2 and x4. All right? So once we do this, we have all the odd index variables in terms of even index variables. We substitute into the equation. So this x1 is written in terms of x0 and x2. This x1 in terms of x0 and x2. So this equation will have only x0 and x2. This equation will have x0, x2, and x4, and so on. So I get another set system of triangular linear equations that have as many equations. And these capital L, capital D, capital U are computed based on lowercase l, lowercase d, and lowercase u using these equations. So let's say a dozen or so arithmetic operations per equation are needed to compute these new coefficients, and therefore reduce the original system of m equations into a system of m over 2 equations. And then we do this recursively until we get to a single equation in one variable. Okay, so here we have m equations in m variables. Let's say m is a power of 2. Here we have m over 2 equations in m over 2 variables, and continue in this way until we get one equation in one variable. Solve that and then go backwards to find the value of all the other variables. Okay, if I were to implement this on a parallel processor, this would be the ideal connectivity for the nodes. So at the bottom, you see the 16 equations, okay? So each of these circles at the bottom holds one of those equations. So this one has x0 as the middle variable, this one has x1 as the middle variable, and so on. So this one has an odd index variable. It computes x1 in terms of x0 and x2 and substitutes it in the equation held by this processor and in the equation held by this processor. This one computes x3 in terms of x2 and x4 and then substitutes it in these two equations. So these connections are basically what we need in order to form those new equations. So I started with 16 equations, then I have 8 equations here. I repeat the same process. So this is now an odd index variable in among these 8 variables. Okay, I have 0, 1, 2, 3 if I renumber. So this one now computes x2 in terms of x0 and x4 and transfers that what it found to these two. So I now have 4 equations with 4 unknowns, 2 equations in 2 unknowns, 1 equation in 1 unknown. x0 is computed. And once x0 is computed, is substituted here, x8 is computed. Once x0, so we go downwards, back towards the original equations. x0 and x8 computed allow me to compute x4 and x12 and so on until all the variables are known. Okay, because these equations are, say, x1 and x3 in terms of x0 and x2 are computed in parallel, they're two separate processors, it takes constant time for every level that we go up, and it takes constant time for every level that we return. Therefore, this will require logarithmic time. Okay, so I've redrawn this diagram here with some of the links shown in dashed format to show you that basically an X tree is a tree structure in which nodes on every level are connected to each other as a linear array. So this is the root. These are the 2 children of the root that are connected to each other. These are the 4 children at the next level that are connected to each other, and so on. So an X tree basically provides the connectivity that we want for solving. It actually has more links. So basically connect this to this, connect these four together, and so on. Now, some links do not exist in X tree. So in an X tree, X8 is connected to these two, X0 is connected to these two. So this link does not exist in an X tree. But that doesn't cause a problem because that link basically can be emulated whenever you need to communicate along this link. You can communicate along this link and then this link. So it will be a little bit slower, but you can still do the same things in the same asymptotic time. Okay? I can even simplify the X tree by removing all these diagonal lines and just keeping the vertical lines and horizontal line. And this will be called a 2D multigrid. So a 2D multigrid can do the same job as X tree with some slowdown. So for example, this link no longer exists in the multigrid, but we can do the same communication in 2 steps. Okay, this one doesn't exist, we can do. So a multigrid is basically an X tree in which we have kept only the vertical lines and the horizontal line and have removed all the diagonal lines. Okay, so this is basically an architecture for this odd even reduction. This is kind of wasteful because, when this row does its computation, then it sits idle because the computation moves to this row, and then this one sits idle while this one works. Okay, so we are using too many processors. But what if we use a linear array? It turns out that we can do the same computation rather efficiently on a linear array. Initially, the linear array basically does what these nodes in the X tree or in the 2D multigrid would do. Then in the next step, every other processor will be active. Okay, so in the next step, X0, X2, X4, X6 will be active. And then communication between them, instead of being in one step, as was the case there, will be in 2 steps. So from here to here, the 2-step communication process and 2 steps in this direction. So the communication time, instead of being 1 plus 1 plus 1 plus 1, will be 1 plus 2 plus 4 plus 8. So it will be 2m minus 2. M minus 1 going up and m minus 1 coming down. Okay, so we can perform that algorithm on a linear array using order m time. Okay, so the algorithm, remember, oh, maybe I didn't mention that. How much time do you need solving this in using a sequential algorithm? This green part of the slide that I skipped. So T for m equations, T for m over 2 equations, these ones, plus a linear amount of time, because each equation needs a constant number of arithmetic operations, and therefore that will be Cm, and the solution for that would be 2Cm. So the sequential algorithm requires linear time. Okay, the linear array also needs linear time, so it's not particularly efficient because it's not doing substantially better than the sequential algorithm. Of course, the constant in this case is smaller, it's only 2, whereas in this one, the constant basically is the amount of arithmetic that you need to do for doing these reductions. Okay, so the C is larger here. Okay. Now, if you do the odd-even reduction on 2-dimensional mesh, you can achieve better speed up. So here I've shown, so basically I map this linear array of 16 processors onto a 4 by 4 mesh. So this is the original numbering: 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So initially, each of these processors has one of the equations. Then 0 needs to communicate with 1, okay, and 1 with 2. I should say 1 would communicate with 0 and 2, but those are neighbors, so it takes just one step. Then in the next step, 2 will communicate with 0 and 4. Okay, 2 would communicate with 0, that's 2 steps. With 4, it will be 3 steps, but let's ignore that for now. So 2 steps. And then when we get to here, where it would require 4 steps on the linear array, it requires 1 step on the mesh. So 0 will be communicating with 4. Okay, or 4 communicates with 0 and 8. Okay, 4 communicates with 0 and 8. Okay, and if you add up these communication steps, it will be order square root of m. So running time, I'm still using m processors, but the running time, instead of being order m, becomes order square root of m. And we know that order square root of m is optimal for a square root of m by square root of m mesh, because the diameter of the mesh is order square root of m. Okay, solving an arbitrary system of linear equations, one way to do it is using Gaussian elimination. You probably remember how to do this. In this example, I'm basically solving 2 systems of linear equations at once. I can do that provided the matrix of coefficients is the same for both of these. So 2 for -7, 2 for -7, 3, 6, 10, 3, 6, 10. So the matrix of coefficients is the same. The right-hand sides are different. Okay, I can solve both of these at once through Gaussian elimination. So the way I do that, I write the matrix of coefficients here, then the right-hand sides. So this is known as the extended matrix A prime. So this is the matrix A. I add the right-hand side. So if I just wanted to solve this one, there would be just one column added. Okay, then I try to convert this matrix without changing the solutions into a matrix such as this one, where the identity matrix sits here. And then these now have been transformed into the solutions. So the first set of equations has the solutions -2, 0, -1. And the second set of equations has the solution 0, -7, -5. So these transformations are done from this initial matrix to this matrix, basically aiming to put the identity matrix here, by operations that do not change the solution. So for example, if you take this equation and multiply all the terms by 2, if you write 4x0 plus 8x1 minus 14x2 equal to 6, it's still the same equation. So I can multiply rows by constants, and I can also combine rows by subtracting some multiple of one row from another row. This is basically, in terms of equations, like subtracting a multiple of this equation from this equation, and that's a valid equation. It has the same, satisfies the same solution. Okay, so here's how I do it. In order to change this 2 to 1, I divide everything in the top row by 2. So I get 1, 2, -3.5, 1.5, 3.5. So I already produced that 1 that I'm looking for there. Okay. Then, in this case, because this next row has a 0 here, that causes trouble. I have to switch these two rows because I want to subtract the multiple of this row from this row to make this into 0. Remember, my aim is to change that into 0. So imagine this row, these two rows switch. So I have to subtract the multiple of 5 from 2 to turn it into 0. And that's basically 5 times 0.4. So I multiply this row by 0.4 and subtract it from this row. Okay, and so on and so forth. So I repeat this process, aiming to make all these diagonal elements equal to 1, and that's done by division. So when I have 5 here, for example, I divide that row by 5 to turn this into 1. And then in order to turn these elements to 0, I subtract the multiple of another row from here. That other row should have a 0 here because I don't want to change this 1 into something other than 1. Okay, so this is called the Gaussian elimination, and this can be implemented using, this is basically one step of Gaussian elimination. The matrix comes in from above, the extended matrix. So this is the original coefficient matrix. This is the right-hand side for one equation, for one set of equations. And then basically a 0 comes in, assuming that it's not 0. Its inverse is computed, and that inverse is broadcast to all of these cells. Okay, because that tells you by what, when you compute the inverse of this, all the other elements must be multiplied by that inverse, and then a subtraction takes place. So the cell computes what comes in from above minus the product of x multiplied by the z, which is stored by the cell. Okay, and this will be the complete Gaussian elimination. Each row basically does one step of the Gaussian elimination. I won't go into the details of the algorithm. If you're interested, you can read. So the movement of these rows has to satisfy some, it's more complicated than just pushing these values through. Basically, values overtake one another as they go through these columns. Now, in the algorithm, as I described to you, I said that this value is broadcast to all the elements of the row. Now, if I have a large mesh here, then this broadcast requires both long wires and also a lot of energy. The signal has to be strong enough to go through all of these. So you either have a fairly small mesh, or the signal has to be repeated on the way to getting to all these cells. Okay, this is just another drawing with two sets of right hands, so 3 sets. Oh, I'm sorry. Let me go back. So this is basically solving a linear system of equation. This one is matrix inversion. So matrix inversion, as I said, corresponds to basically solving multiple sets of linear equations with different right-hand sides. So one set will have the right-hand side 0, 0, 1, or 1, 0, 0. 1 comes in first. The next one has 0, 1, 0, and the next one has 0, 0, 1. So these are columns of the identity matrix. So this one basically computes the inverse. So this is basically Gaussian elimination with different right-hand sides. And that gives you basically the inverse of a matrix. Okay. Uh, Another way of solving linear systems of equations is through what is known as Jacobi relaxation. Basically, given a set of equations, you can solve the three equations for the different variables. In other words, compute x0 from the first equation in terms of x1 and x2. Compute x1 from the second equation in terms of x0 and x2. And compute x2 from the third equation. So basically you iterate. You take a guess for the values of x0, x1, and x2 and substitute those guesses in these equations and evaluate these equations to get hopefully better guesses or closer values to x0 and x1 and x2. And then you repeat this process. Under some convergence conditions, this method converges rather quickly and you get, so the advantage of this is that basically once you start with the guesses, there's a lot of parallelism, very simple parallelism, because one processor can compute this equation, another one can compute this equation to find the new values of x1, x2, and x3, x0, x1, and x2, and then you repeat the process. So it's very simple to program. The parallelism is of the simple variety, where processors work independently of each other. Okay. Now, a variant of Jacobi relaxation is called Jacobi over relaxation. Now, one disadvantage of Jacobi methods is that sometimes you get oscillations. So, for example, in this set of equations, let's say you start with guesses 1, 1, and 1. You have no idea what the values are. So let's say all three of them are 1s. So you substitute in this equation, find the new values that are 3, 1.834, and -1. Okay? Then substitute these, and then sometimes the values go up, sometimes they come down, they will oscillate in general, and sometimes convergence does not occur. So in order to avoid those wild oscillations, a Jacobi over-relaxation finds a new value of one of these variables, not from that equation, but a combination of the old value and what that equation suggests. So this equation basically suggests a new value. And this is the equation that I used on the previous slide. Okay? And then you weight that by gamma. Gamma is a number between 0 and 1. And then you weight the old value by 1 minus gamma. So for example, if gamma is 0.5, then the new value will be 0.5 times the old value plus 0.5 times the new value suggested by this equation. So by playing this, the smaller the value of gamma, so if gamma is near 0, then the new value of x will be very close to the old value, and this equation will have little effect. So basically, convergence will be slower, tends to be slower. On the other hand, if y is large, in the extreme, gamma being equal to 1, then this term disappears, and this becomes basically simple Jacobi over relaxation, Jacobi relaxation. Okay. All right. So enough of that. A few words about graph algorithms. A graph can be a directed graph can be represented as adjacency matrix, where a 1 occurs in the matrix in position ij when node I is connected through a directed link to node j. So for example, node 0 is connected to 3. That's why in the row 0, column 3, we have a 1. Node 1 is connected to 5. That's why in row 1, the fifth column, I have a 1. In the fourth column, I also have a 1 because 1 is also connected to 4. On the other hand, 1 is not connected to 2. Therefore, row 1, column 2 is 0. So this is known as adjacency matrix. It just shows the connectivity of the graph. Of course, if the graph is undirected, meaning that we have, if there is connection 0 to 3, there's also connection from 3 to 0, then this matrix will be symmetric. Okay. Another way to characterize graphs is when we have weights associated with these links. So you can view this, for example, as 5 cities with distances, or travel time, or travel cost between them. Okay, and that's presented by a matrix in which, instead of just having 0, 1, not connected, connected, says not connected is represented by infinity. Basically, there's an infinite cost to go from one of those cities to another one if there's no direct connection. Okay, and basically the other weights are just written in the matrix. Now, negative weights, the context of roads or distances doesn't make sense, but there are contexts in which negative weights do make sense. So for generality, I've shown a negative weight in this graph. In most practical problems, the weights are non-negative. Okay. Sometimes even 0 weights do not make sense. So if these are distances, then distance of 0 or cost of 0 may not make sense, although it may make sense too. For example, if there's free transportation between these two cities for some reason, then that makes sense, having 0 travel cost. Okay. So one algorithm that is of interest to us, I'll just explain the objective of the algorithm without going into its detail. So given a graph with its adjacency matrix, so the adjacency matrix says which node is connected to which other node by a link. Okay. Now I want to find the transitive closure A star of this matrix, which shows which node is connected to which other node, not necessarily through a direct link, but through a path. So for example, 2 is not connected to 4 through a link, but it is connected through a path of length 2. So in the transitive closure of this matrix, the element 2, 4 should be equal to 1. So row 2, so when I compute the transitive closure, row 2, column 4 should be equal to 1. Okay? Similarly, 4 is not directly connected to 5, but there is a path from 4 to 5. So element row 4, column 5 should be 1 in the transitive closure. Similarly, every node is of course connected to itself through a path of length 0. So all the diagonals of the transitive closure will, so diagonal elements will also be 1. Okay, so how do you compute this transitive closure? Here is a simple idea. Basically, A star is A to the power 0. That's basically the identity matrix. That supplies the ones and the diagonal elements. A to the 1, those are paths of length 1. A squared of this matrix is, of course, if I perform the multiplication with and or instead of with multiply add, then A squared will give me paths of length 2 and so on. I don't need to go to infinity because if there is a path between two nodes, there will be a path of length n minus 1. If there are n nodes, if there is a path, there should be a path of length n minus 1, because otherwise I would be going into a loop. There are only n nodes, so no path will have, no simple path without loops will have more than n minus 1 edges in it. Okay, so that's one scheme, but this requires a lot of operations. We have to compute all the powers of this matrix. So this algorithm that I leave up to you to study if you're interested in. So these red arrows are basically the things that are added to a transitive closure. So first of all, every node is connected to itself, so these self loops are added. And 2 to 5 is connected by a path of length 2. So in the transitive closure, there will be a 1 corresponding to this element, a 1 here, and a 1 here. Okay? So this algorithm is much more efficient than the one involving the powers of the matrix A, and I leave it up to you to study it if you are interested. And we can perform transitive closure on a 2D mesh. Basically that algorithm, because I didn't describe the algorithm, of course I can't describe the mesh implementation, but basically the matrix will come in from above and the rows go through the mesh, and there are some interactions between rows that are shown here. Okay, I can't describe the details because I did not describe the algorithm. And then this algorithm requires broadcasting from some elements of a row to all elements of the row. So for example, in one step of the algorithm, this node, will have to broadcast its value to all the nodes in the row. And because this broadcasting occurs simultaneously in the same cycle, these delays on these lines will be 0. Okay, if I don't want to have the broadcasting and long wires, I can increase these delays to 1 so that this one basically sends its value to this one in the first cycle. That value proceeds to the next one in the next cycle, and so on. So eventually all the nodes will receive this value, but not simultaneously. So there's no broadcasting. And this is basically done through what is known as retiming. You can always eliminate broadcasting and replace 0 delays on your charts with non-zero delays by retiming. So what is the retiming notion is described here. And if you have a circuit with delays on these lines going between the right side and the left side, and the left side and the right side, so there are some delays there, the operation of the circuit doesn't change if you increase these delays from right to left by some amount d, and you decrease these delays by the same amount d. So basically this left side of the circuit receives everything from the right side d time units later. So basically the primary input should be delayed too. Everything that comes into this part of the circuit comes d times unit later. But because we have reduced these output delays by d, this part of the circuit receives its signals at exactly the same time as the original circuit. So everything is delayed into this part by d, and everything coming out of this part is advanced or speeded up by d time units, and therefore this circuit still works correctly. So in the case of the algorithm that we just discussed, oops, okay, oh, for some reason this is not moving to the next slide. Okay, just 1 minute. Let me see what's going on. Okay, maybe I should end show and then sorry about this. I don't know what happened. That let me go back to where we were. Okay, and then okay. So the solution that I did not describe to you, the timing is like this. So there are these broadcasts. See, this cell broadcasts to the entire row. The next row, this cell broadcasts to the entire row. And the next one, this one broadcasts. And then by retiming, basically this 0 is changed to 1. So this signal comes into this cell 1 time unit later than this original implementation. So I delay this input also by 1. So these two now arrive at the same time. Okay, and if you apply this retiming lemma repeatedly, you get this retimed circuit in which no 0 delays exist. So for example, in going from here to here, there's 7 units of delay, and also through this path, 1 plus 1 plus 5 is 7. So all the signals that come into a particular cell arrive at the same time, although a bit later than, or maybe a lot later than the original circuit. And using this trick, I basically removed all the 0 delays. This is a very important technique in designing VLSI circuits. So that's why I discussed it, even though the algorithm itself was not discussed. Okay, the last algorithm in this chapter is image processing, basically finding connected components. So I take images to be basically black and white pixels. So black, I've used different shades, orange and green, but they're all black, to emphasize that basically this image contains two connected components. There's this line, and connected component is basically a bunch of pixels that are adjacent, either horizontally, vertically, or diagonally. Okay, so this is connected to this one, this is connected to this one, and so on. So all of these are connected to each other. That's one component. And this is another connected component, which happens to be the approximation of a circle. And these two components are not connected to each other because of this empty cell there. If this pixel were also black, it's X pixel, then there would be just a single component, because this separate component now would be connected to this component. Okay, so an idea to find connected components is basically to propagate information for with cells communicating. So for example, this one is a component. Initially, this is a separate component. They exchange information and they realize that they're adjacent, therefore they are part of the same component, and so on. So this information about these two find out that they're part of the same component, then these two find out that they're part of the same component, and therefore all three of these, and so on. Now this is a bad algorithm, because in the worst case, when you have this connected component, the orange in this diagram, it takes order p time for information to propagate from this end of the component to this end of the component. Okay, we hope to be able to do an order square root of p, not order p time connected component. Okay, so I'll show you a recursive algorithm. Basically, it says given this mesh with various, this one you can easily see there's one component here, second component, the third component is this huge component over here. So it has 4 components, okay? How do I go about identifying these components? I do connected components in quadrants, so it's a recursive algorithm. So these are connected components in this quadrant. There are 3 of them. There's 1 connected component in this quadrant, 1 in this, and 2 in this. Okay, so I find the connected components in quadrants and then try to merge them. And merging basically is for these cells across these boundaries, exchanging information. And so this is component 0. I basically use the smallest processor index as the component index. So processor 0 is here. So this component is called component 0. Processor 3 is there. This is component 3. Processor 26. So this is component 26 and so on. And then these two exchange information, and this cell figures out now that component 4 is the same as component 3. They're connected. So this information now propagates by broadcasting across the row. So this one figures out that 4 is the same as 3, and then informs all the cells, processors in that half row, if they are part of component 4, to change to 3. This one similarly figures out that it's part of component, this one remains component 3, but this one discovers that it's part of component 3, so it broadcasts information. Okay, so details I won't supply. The merging of these requires order square root of p of time, and therefore this recurrence says that the total time is order square root of p. Now there's also this very elegant algorithm due to Levialdi, who basically devised an ingenious scheme. So this particular mesh has 2 connected components. You see that this is 1 connected component, and this is 1 connected component. Okay, so Levialdi's algorithm works by basically shrinking these components until each one becomes a single point. So this has a little bit more to go, a few more steps. This one has already shrunk to a single component. This one has not. It will in a couple of steps. So the shrinking process is dictated by this algorithm. It says if there's a 0 and there's a 1 above it and 1 to the left, regardless of this other, the third, that one can be 0 or 1. So as long as there's a 1 above and a 1 to the left, this 0 will be changed to 1. If there's a 1 and it's surrounded by 3 zeros on top, on left, and diagonally here, that one will be changed to 0. Okay, so you see, for example, here, this one has 3 zeros according to this rule. So this one in the next step will be changed to 0. On the other hand, this 0, because it has 2 ones above and to the left, will be changed to 1, and so on. So I said I characterize this as shrinking. Actually, sometimes the components grow. As you see, this one is a little bit thicker than this one. But eventually they will shrink into single points. And at that point, those single points are the components that we are looking for. And then we go backwards and basically label all the other points that were deleted in this process as being part of this component and so on. Okay, so I won't describe the details in the interest of there's a proof here that this algorithm works. So let me go to chapter 12 and discuss a little bit some of the ideas in this chapter. So first of all, we talked about 2D mesh. We can have 3, 4, 5, 6-dimensional meshes. Let's talk about 3-dimensional meshes. Now, it may occur to us, okay, because space is 3-dimensional, we should be able to build 3-dimensional meshes. And the diameter of a 3-dimensional mesh is smaller for the same number of processors. It's basically cube root of p, order cube root of p, instead of order square root of p. Okay? However, we can't really build, at least not at present, a truly 3-dimensional structure. There are some, 3D ICs being built, but on a limited scale. Most integrated circuits in modern IC technology are really 2.5 dimensional. In other words, if I want to build an 8 by 8 by 8 mesh, well, one layer of that mesh, which is 8 by 8 2D mesh, can be easily laid out on the printed circuit board using short wires and pretty nicely laid out. However, the next layer of the mesh will be on a different board, and connections between this layer and that layer will not be equally short because wires have to go to the backplane, travel over the backplane to the other board, and then on that board. Okay, there are some suggestions that perhaps we can connect this processor on this board, this processor, the corresponding processor on the next board using optical interconnect. That's feasible, but it's not cost effective at present to do that because it requires a lot of circuitry to basically implement the optics, optical transmitter, optical receiver, and so on. Okay, so because our IC technology is not truly three-dimensional, so a 3D mesh has some advantage theoretically because its diameter is lower. But once you implement it in this way, much of that advantage evaporates. And therefore, really, two-dimensional meshes are much more practical at present than three-dimensional meshes. And of course, higher dimension is even less. Higher dimensional meshes are even less practical. Okay. So if we could build a three-dimensional mesh, and so this is basically an indexing scheme for the nodes in Z, Y, X order. So Z, X, Y, and Z are these three dimensions, X, Y, and Z. Z, Y, X order simply means indices. First, the X is changed. So 0, 0, 0 goes to 0, 0, 1. 0, 0, 2, 0, 0, 3. So this is a 4 by 4 by 4 mesh. And then Y changes next in the indexing scheme. And then eventually Z changes last. So for example, when you do row major order, so you have YX order. In other words, in X dimension, the horizontal dimension changes occur first, 0, 1, 2, 3, and then you go to the next row and continue the indexing. So this is basically a generalization of row major order. Okay, assuming that we could build a 3D mesh, sorting on 3D mesh is fairly simple. Remember that in 2D mesh, shear sort was not optimal. Okay, well, it turns out that on 3D meshes, we can devise an algorithm similar to shear sort, which is also optimal. And that's a surprise. because one would think that sorting on a 3D mesh would be more difficult than on 2D mesh. And this is an algorithm that does that. It has 5 phases, so there's no iteration involved. It said sort elements on each ZX plane into ZX order. So ZX plane is basically this plane. So let's say the front processors, then the middle processors, then the back processor. That's the ZX plane. Sort elements on each YZ plane into ZY order. So YZ plane is this one. So this is a YZ plane, and so on. Sort elements on each XY layer into YX order. So these are basically 3 2D mesh sorts. Okay. There's another 2D mesh sort down here. And between those, we have applied 2 steps of odd-even transposition. Okay, so the running time of this algorithm is 4 times the running time of a 2D mesh sort plus 2, these 2 steps. Okay, and this is optimal because it's order cube root of p. And the diameter of this mesh is order cube root of p. So that's a pleasant surprise that you can sort much more easily on 3D meshes than on 2D meshes. Okay, so matrix multiplication I'm going to skip on 2D meshes, on 3D meshes. So there is basically this discussion whether we would be better off building a 3-dimensional mesh knowing that one of those dimensions would be slower in terms of communication than the other 2 dimensions, given that we have a 2.5 dimensional implementation technology. So here is a 3 by 3 by 3 3-dimensional mesh. I can also emulate this mesh on a 2D mesh by putting the layers, so the upper layer, these 9 processors up there, so here, the middle layer, and the lower layer. So any communications within the layers can be done just as fast on this 2D mesh as there, because the layers are basically mapped one-to-one into a 2D mesh. Okay, now if I want to communicate between the upper and middle layer, let's say between this processor and this processor, I would be communicating between this processor and this one. Okay, so those are some distance off, and therefore that communication will be slower. But then communication would be slower even in the 3-dimensional. So it's a question of which one comes out ahead. And generally speaking, experience shows that 2D meshes generally perform better. One advantage of 2D meshes is that each processor has 4 neighbors, whereas in the 3D mesh, each processor has 6 neighbors. So if we have a certain communication bandwidth to divide between 6 channels here versus 4 channels here, then we can make the channels wider here, higher bandwidth, okay? So that sort of also compensates for some of the lower performance of 2D mesh, theoretically lower performance compared to 3D mesh. All right. We can have stronger or weaker connectivities. These are examples of stronger connectivity. Instead of each node having 4 neighbors, as in regular 2D mesh, it has 8 neighbors here. And this may seem particularly suited to image processing, because if I have a pixel here, then all the neighboring pixels are directly connected to this pixel, and I can check the neighboring pixels more easily. Again, experience shows that this additional connectivity, now notice that each processor has 8 channels, therefore with the same number of wires, the width of these channels will be half that of a 2D, regular 2D mesh. And this is hex mesh, where each node has 6 neighbors. Okay, so these are examples of meshes with richer connectivity, more connectivity. This is an example of a mesh with lower connectivity or sparser connectivity. By making the channels between nodes unidirectional, so if this were a bidirectional channel and I wanted to communicate at the same time over both directions, I would need twice as many wires, okay? Making it one directional, I save on the number of wires, and I can still send messages between processors. This is called Manhattan Street Network because these unidirectional communication in rows going in this direction, left to right in one row and right to left in the next row, resemble the streets of Manhattan, where every other street is one way in, in a different direction. So, for example, if this were a bidirectional mesh, I could go from this node to this node in one step. But because I've made these links directed, I can't go directly from this node to that node, but I can go in 3 steps. This is like going around the block, so to speak, in a car, because this street is one way and this street is one way. Okay, so sometimes distances increase because of this restriction. But again, remember that because I have only 4 channels rather than 8 channels, 4 unidirectional channels as opposed to 8 unidirectional channels. For each node, I can make the channels wider and therefore higher bandwidth. Okay, so experimental studies have shown that this performs very well on many applications compared to a regular torus. Okay, more than 2 decades ago, a PhD student at UCSB, Ding-Ming Kuai, studied under my direction what we call the pruned network. So here I've shown a 3-dimensional torus in which the z direction link are kept intact. So all the links in the direction z are there, but direction x and y links are pruned, or half of them are removed. In the sense that the top layer has only links in direction y, no links in direction x. The next layer down has links in direction x, but no links in direction y. So what this does, it reduces the node degree from 6 in a 3-dimensional torus to 4 in this pruned version. And therefore, just like Manhattan Street Network, you may not be able to go between 2 nodes directly. So from this node to this node, in the original 3D torus, you could go in 1 step. Now you have to go in 3 steps. Okay, so some distances increase, but again, because this is now, it is still a 3-dimensional structure, but it takes much less area to lay it out in 2 dimensions. And therefore, some of that disadvantage of longer distances will be compensated for both by wider channels that we can have, because there are only 4 ports per processor, and also by the easier layout, more compact layout of the structure in 2 dimensions. Okay, this one I'm going to skip. Another idea is that one of the disadvantages of meshes is that the diameter is fairly large. So if you have a 100 by 100 mesh, the diameter is almost 200, okay? That's 198 actually, so almost 200. So it has a large diameter. So the idea arose that we can provide these bypass links so that if a message wants to go, say, from one end of this road to the other end, instead of going 1, 2, 3, 4, 5, 6, 7, 8 steps, it can just take 2 steps, 1, 2. Okay? Well, this is nice theoretically, but it gives rise to some problems. First of all, notice that all the processors on the row have 2 channels at degree 2. This one has degree 4, so it causes some non-uniformity among the nodes. Second, these longer wires tend to be slower, so it's not that, I've reduced the 8 steps to 2 steps. These 2 steps are sort of longer steps, okay? So the analogy here is that we can have a one-way street with traffic lights. Those sort of model the delays in going from one node to another one, and a freeway parallel to that one-way street. So whenever I want to go a long distance, I get on the freeway. And then I exit, and then, so if I want to go from this point on the one-way street to this point, I take the freeway, and then maybe a little bit on the one-way street. Similar here, if I want to go from here to, let's say, here, I take this shortcut, and then 1 or 2 steps maybe using the regular mesh links. Okay, so that irregularity can be cured in the following way. So suppose these are rows of a mesh, okay, and then this doesn't have any extra links, but I can use extra links in the column for that. So I can arrange these bypass links so that they add maybe 1 link to each node. Say 1 link added to this node because of this bypass, 1 link added to this node, and then this one uses bypass in the column direction. So I can make them regular, but still the problem of layout and these long wires is a problem. Now, assuming that I can use buses, several ideas come to mind. So here I use the mesh with its local connections as usual. Okay, but I also have this bus that connects everything together. Of course, if I want to connect all the processors together with a single bus, the number of processors cannot be too large. But let's ignore that for a minute. So a bus can carry 1 message at a given time, okay? So if this corner processor there wants to send a message to this corner, it can do it over the bus, and it gets there much faster than if we use the regular mesh connections, okay? However, we can do communication between this corner and this corner simultaneously between this corner and this corner because there's just 1 bus. Okay, I can develop an algorithm. So this bus in fact helps even though there's just 1 bus. I can do semi-group computation in order cube root of p instead of order square root of p. And the idea is that I do semi-group computation in these cube root of p by cube root of p submeshes. And that takes order cube root of p because these are small meshes. And then the number of elements, these yellow elements that are the result of that semi-group computation, is cube root of p because there are p to the 2/3 elements in each of these meshes, p to the 1/3 times p to the 1/3. And therefore there are p to the 1/3 such meshes, and therefore there are p to the 1/3 results from those meshes. And I can combine those one at a time by using the bus. Basically, each of these processors sends its value, let's say, to this corner processor. This one sends, then this one sends, and so on. And then that one computes the final result and then broadcasts it to all the processors. So p to the 1/3, order p to the 1/3 time for these partial results, order p to the 1/3 time to combine them, and then just one step for broadcasting. Okay, so that single bus help. Now, if we have too many processors to connect them to a single bus, an idea is to use separate row and column buses. So the black buses here connect processors in rows, and the orange buses connect processors in columns. I can still do long distance communication, not in one step, but in two steps. So for example, a message wanting to go from this corner to this corner can take one step over that bus to this corner, and one step over this bus to this corner. And I won't describe this algorithm. It turns out that with these buses, now I can have larger meshes. So even if I have a, say, 30 by 30, 32 by 32 mesh, it's feasible to connect 32 things to the same bus. Okay, so the running time for the semi-group computation now reduces to p to the 1/6, which is much, much better than p to the 1/2 square root of p, the original time, or p to the 1/3 when you had a single global bus. Okay, section 12.4 I'm going to skip. Now, pyramid is an architecture that is derived from a mesh. So the base of the pyramid is a 2D mesh, but then there are 2D meshes as we go up. So there's a 4x4 mesh at the bottom, there's a 2x2 mesh in the middle level, and a single node, the apex, at the top. And the nice thing about the pyramid is that, well, it has all the capabilities of a mesh at the bottom, but also there are paths of logarithmic length between any two nodes. So from this corner to that corner, I can go up the pyramid to the apex and then down. So this is log plus log, 2 log m, so it's logarithmic latency. But on the other hand, if too many of these long distance communications are performed, then the apex becomes a bottleneck and messages will be delayed. This is a two-dimensional layout of a pyramid. This is a 2D multigrid, which is basically a poor man's pyramid. Instead of the apex being connected to all 4 of these nodes, it's connected to just one of them. Similarly, this one, instead of being connected to 4 at the lower level, is connected to just one. Now, the original pyramid has node degree 9, because in general, each node will have, okay, it doesn't occur for this small pyramid, but if I had a larger pyramid, each node has 4 neighbors on its own layer. It has 4 neighbors on the lower layer, and then 1 neighbor in the higher level. Now this one reduces the node degree because it's now 5, now 6, sorry. There is 4 neighbors in the same layer, 1 neighbor above, and 1 neighbor below at most, okay? So it reduces the node degree. Okay, the last architecture that I'll just define for you without going into much detail is mesh of trees. This is really not a mesh. It looks superficially similar to a mesh. It's not a mesh. It's called mesh of trees because, so we have a two-dimensional array of processors at the bottom. They are not connected to each other as a mesh. They're just independent processors. They are connected to each other through row trees, trees constructed on rows, and column trees. And here I've shown just one row tree. There will be another row tree for this row, another for that, and so on. and I've shown just one column tree for column 0, there will be another column tree. Okay, so the base elements are not connected directly to each other except through these trees. So again, the nice thing about this architecture is just logarithmic diameter. So if I want to go from this corner to that corner, I go through the column tree to this corner and through the row tree to the other corner. Of course, here I don't save much because this is a small uh, configuration. I'm using 1, 2, 3, 4 to get there, 1, 2, 3, 4 to get there. Whereas if this were a mesh, I would need 1, 2, 3, 4, 5, 6. So a mesh would have been better. But if this becomes much larger, then the advantage starts to materialize. And this is a 2D layout of this mesh of trees in which you see the row trees, the orange nodes connect rows into a tree, and the yellow nodes are column trees. Okay, so, and this is another view of it. Again, you see that the orange nodes form the row trees, and the yellow nodes form the column trees, along with the base nodes that are white. This is another drawing of 2D mesh of trees that shows that it is possible to use it as a processor to memory interconnection network. So if you have 4 processors and 4 memories, okay, basically the 4 processors are the roots. The 4 processors are these roots, the orange roots. And the 4 memories are these roots, the yellow roots. And they can be viewed as a permutation network, basically. Any permutation between the processors and memory modules can be implemented. So it's sort of like a crossbar switch. All right, so let me stop at this point. There's an algorithm here that you don't need to study. So actually several simple algorithms and then minimal weight spanning tree algorithm. I'm going to skip those and you are not responsible for them. All right, this concludes my discussion of chapters 11 and 12, and basically coming to the end of part 3 of the textbook. We'll start part 4, beginning with lecture 13 next time. All right, goodbye for now. Stay safe until we meet again in lecture 13.